Hello, this project is on hydraulic jumps by Joshua and Jesus. A hydraulic jump is defined by a supercritical flow, a flow of high velocity, to a subcritical flow, a flow of low velocity, which causes an abrupt change in height. The most common example of this is when you turn on your kitchen sink. There's a thin layer of fast-moving water and then a hard transition to slower, deeper water. Hydraulic jumps occur naturally as well, like in whitewater rapids. The water in the river flowing over rocks changes velocities, causing jumps. In engineering applications, they are often used in dams and mills to dissipate energy to limit damage and structure in the environment. So to create the hydraulic jump, we created a rectangular channel outfitted with a water reservoir and a sluice gate on one side and an obstacle downstream to create subcritical flow. We also set it on about an 11-degree incline to increase the speed of the flow and the size of the jump. On the bottom of the channel, we marked 1-inch squares to help us calculate the velocities off of our recordings and determine where the jump occurs. Our experiment consisted of 3 tests and multiple trials within those tests to determine the initial velocity, final velocity, and the jump height. The 3 tests only differed in the initial speed, which we controlled by the sluice gate. Here's our design in action. Here you can see the supercritical flow, which has a height of about 1 inch, 0.1 inch in thickness, and the abrupt height change in the jump.
On this slide, we have some of the equations we use for our calculations. First, we use the fruit equation, which can result as greater than 1, meaning it's supercritical, equal to 1, where it is just critical, or less than 1, where it is subcritical. Next, we plugged in these fruit numbers into our depth ratio equation to be able to solve for our jump height. In this case, it was y2. And then we also used the conservation of mass equation in order to be able to solve for the velocity after the hydraulic jump. We also included the head loss equation because we know that there is going to be some energy lost in this transfer. On the right hand side, you can see the MATLAB script that we used in order to compile these computations and yield the results that you see at the bottom. Comparing the first fruit number to the second fruit number in each test, we can conclude that we indeed do have a hydraulic jump in each case. On this next slide, we have tabulated the results where we took 3 different initial velocities in order to calculate the varying jump heights. We took measurements throughout our tests and compared them to the 3 theoretical calculations from our MATLAB script. We can see that we have a percentage error ranging from about 12 to 19%, decreasing as the jumps got bigger. This could be a result of inaccurate measurements, minor turbulences caused by varying amounts of hot glue, and then we can also attribute some of this variation to the head loss that we also calculated within our script. Overall, we have come to the general conclusion that an increase in an initial velocity will result in an increase in the hydraulic jump height as well. Thank you for listening.